the full screen. Let's put this in the old science cart. Okay, so this video is pure practice, pure mechanical practice, mostly for my class, getting ready for a final exam. And all of these graphs will be on there. And I expect my students to be able to write these equations in 10 seconds or less. And to get there, we just practice, a lot of reps. So I'm gonna hold down conversation to a minimum here. Just gonna, you pause the video. I've got equations of lines here through 2 points. All right, so let's just have at it. I said I would keep everything to a minimum. So we're looking at this first picture here. And so I'm going to build off of 3, 5. So x minus 3 plus 5. The change, the linear change from 3 to 7 is 4 units. And the change from one y to the next is 3. And there we have it. So there's the first. I'll erase that equation and I'll write right above this one. To make sure you can see this, I'll center it a little bit more. So I'm going to build off a 9, 2. So x minus 9 plus 2. And I'm going from 9 to 12, which is a change of 3. And I'm going from 2 to 1, which is down 1. And that's that equation. Next one. I'm going to build off of -8. So I'll write x plus 8. And that takes me to the number 4 when I plug -8 in. -8 to -6 is up 2. 4 to 11 is up 7. And that's that function. Remember, you're pausing the video. 1903 to 81. X minus 1903. Plug that in, get 0, but we want 81. And we're going to go from 1903 to 2024, which is 97, 107, 117, 121 years, I believe. And 81 to 90 is 11. No, 9, sorry. I was already thinking about 11 squared there. All right, so those are the linear calculations. Now we're going to go to the quadratic. I'll probably, at least for a couple of them, do some roots. But supporting video, quadratics, the geometry of change dives into a little bit more about the salient characteristics of a quadratic. Certainly not all of them. It's an exhaustive discussion. I am going to write the equation based on square change from -2. So there's my square change from -2. And from -2 to 4, square change of 36. I don't want 36 units of square change, 7 to 16. 9, I'm not going to reduce fractions here. So that's that one. Oh, I should have gotten you the roots there. And maybe I won't do roots. 267, so I've got x minus 2 squared and 67 to identify the vertex. From 2 to 0 is 4 units of square change. When I put 0 in, I get 4 units, and 4 units plus 67 doesn't take me to 3, but going down 64 does. So maybe I'll do this root because that's such a nice round number, -16. All right, so where are the roots? They're down here. They exist, so I know they're real. One number I know does not work is 2, but I'm going to go left and right to get this x and that x. So here's 2. I'm going to go right and left, therefore the plus minus. From 67 down to 0 is down 67 units. Got to put it inside a square root. I got to go down 67, but my multiplier is -16, and those are your roots. All right, so now pause the video. Let's go 2019. So we've got x minus 20 squared plus 19. And I'm going from 20 to 30. That's 100 units of square change. And I want to get from 19 to 47, which is 28 units. And we'll leave it like that. That's our y equals. All right, last one for quadratics. Last one. All right, so y equals measuring square change from -15. I'll use that. Takes me to 100. How do I get from 100 to 93? I got to go down 7. Got to go down 7, and my square change from -5 to -3 is 144 units. All right, so I'll show that one here. I'll plug -3 in. -3 plus 15 squared is where that number is coming from, because that does not work. That number does not work when I plug -3 in. So I cancel it out, and I take 7 away from 100, takes me to 93. Okay, let's make sure I center the video, absolute value. We write absolute value in piecewise functions, so there are supporting videos on the channel for that, solving inequalities using the pieces. But this is just practice writing the equations. Let's clean this off. Absolute value from 8, x minus 8 plus 3. So this is going to be absolute value change from 8 to 15 is 7. Canceling that out. 3 to 100, I want to go up 97 units. So that's that one. Y equals. Pausing the video, you try the next one. I can write right above it. -4 gets me 7, so x plus 4. Smallest distance you can travel is 0. So I'm always making a 0 out of that first number. And I want to get from 7 down to 2, so I'm going down 5. And the absolute value change from -4 to -20. So -4 to -20 is 16 units backwards. Right? But the absolute value of that is going to be positive, but the multiplier is negative, V-shaped down. All right, let's get rid of that one. Okay, if I make a mistake, I make a mistake. I'm just going to plow through. 7, -2, so x minus 7 minus 2. Absolute value change 4 units, and -2 to 17 up 19. So that's that one. Pause the video. You try that one. Y equals absolute value of x plus 100. Always making a 0. Gets me 47. V-shaped down, so I know it's a negative. 47 to 42. I'm going down 5. Minus 100 to -1 is the absolute value of 99. So that takes care of that one. All right, next batch is square roots. Get the trusty cart to keep moving around here. And just a couple of quick things about square roots. Let's see, we got that so you can see it. Can't tell if this is blurry or not. But square roots are the side lengths of squares. Descartes' coordinate system. We work with real numbers, although big discussion about that being a real number. Well, we express it as an imaginary, then we don't graph that on this plane. Although x squared equals 9, it's worth noting that that hits 9 on a positive and a negative, and it may not hit -9, but if you flip it over, you get the same magnitude answers, right? That x is the same magnitude as this x. Right, same one, except we would say that this is positive 3i. Imaginary intersection, negative 3i. And I'm not sure that, that I-axis from the wall does justice to what really this is all about, which is a sign change. If I change the multiplier, the sign of the multiplier, instead of cup shape up, cup shape down, and then we have some intersections. All right, so square root of 0 is critical, right? I can keep making this square root smaller and smaller and smaller until I get 0 times 0, which is 0. So the square root of 0 exists, and that's what I'm going to make out of the number 5. So I'm going to do the square root of x minus 5 plus 7. Maybe you're already seeing the pattern from the previous problem. I'm going to get rid of square root change, which in this case is 23 units. Because when I drop a 28 in, I get the square root of 23. And that number, square root of 23 plus 7, does not take me to 9. So I get rid of that number, and I take the number that does get me to 9, which is 2. 2 plus 7 gets me to 9, because I'm creating the number 1 right there. All right, so that was just a little mechanics. So 7 and 9, 2. That's my y graph. Okay, so I can erase that one. Looks like -4, so I'm going to write square root of x plus 4, gets me 14. This is going to be my graph. -4 to 1 is square root of 5 units of change. 14 to 11 is down 3. Okay, it's that one. Pure practice here. Y equals. Well, previous video, I talked about reflection, so instead of x minus 7, I'm saying 7 minus x plus 11. Now when I drop a 7 in, I get the square root of 0. All right, and now I'm going from 7 to 0, which is back 7. But when I plug in 0 here, I get the square root of 7 change. And I want to get from 11 to 20. I guess I got to go up 9. That should be that graph. Pause the video. You try that one. 10 seconds or less. Square root of x minus 15 plus 20. Square root change is square root of 6. And I don't want that change. I want to get from 20 to 50. I want to go up 30. Okay. 30 could have been written as 5 times root 6 divided by root 6. So that could have been written as 5 root 6 just for play. All right. Now we move along to exponentials. 10 seconds or less. All right. So let's get this off the board. All right, so can we see where I'm going to write this? I guess I got to write it here, but I'm looking at this one. So everything, all my y values are above 3. How far is it from 3 to 8? 5 units. Next time it's not a differential of 5. There's my first differential. My next differential is 3 to 13, which is 10. And we can see that we have a doubling type function here. X minus 1900. And from 1900 to 2004 is 104 years. And this model is based on 2 principles. The b to the 0 is 1. So we're making a 0 out of this exponent when I plug in 1900. And b to the 1 is b. That's allowing me to do this. All right, so now, pause the video. You try this one. We got a decay problem. But I'm going to build it off of the number 10. How do I get from 10 to 50? I go up 40. Next time I don't go up 40, I go from 10 to 17, which is up 7. And time. I'll go t this time. T minus 1907 because it's years. 1907 to 2024 is 93, 103, 113, 117. All right, and so that's that graph. Now we're going to do the pizza in the oven. I don't do this too often, but it shouldn't be a problem. We usually just do Newton's law of cooling type problems, but let's put the pizza in the oven. Of course, the pizza never was going to negative infinity on this end for temperature, but let's just build a function that we see. I'm going to build it off of 350 degrees oven temperature. To get to 40, I got to go down 310 degrees. Oops. And then I've got to go down, so that's down 310. This one is down how much? Down 50, right? Down 50. So the next one is not down 310, it's down 50. So negative into negative, I'll just write 310, 50. Obviously that can be reduced, but we're not going to write here. So time, x equals 3 minutes, 12 minutes. So in terms of minutes, let's go t in terms of minutes. Minus 3, let's do minutes, do some subscripts, and 3 to 12 is 9 minutes of change. And so you can see how minutes turn into Fahrenheit temperature. Okay, so that's exponential. Now we're going to do some logs, and the logs are based on 3 situations. 0 is undefined. We need positive numbers inside the parentheses. We put a 1 inside the parentheses, we get the number 0. Love to multiply by 0. And b to the b, right? What do you put on top of b to get b? The exponent's 1. And I like to multiply by 1. I don't think I need a calculator to multiply by 0 and multiply by 1. So that's what this is all based on. So in this case, we want to start with our y values again. And the first y value I see is 1803. How do I get from 1803 to 1900? Boy, I like 97 today. I see a logarithm. And I want to make a 0 out of the number 3. x minus 3. What that means is places on the curve are changing by certain amounts, right? To get on the curve, I've got to move 2 units over. So when I put 5 in, 2 divided by 2 is 1, which makes it 0. Doesn't matter what the base is yet. Gets me 1803. And when I drop an 11 in, I get 11 minus 3. 8 divided by 2 is 4. But I'm going to do 8 divided by 2 right there because I think you can see there's something to learn here. Okay, so that's that one. All right, now we'll do this one. Y equals 1504. I knew a lot of people back then. 1504 to 1600. Oh, I changed up 96 years. Oh, and this is a logarithm. And I want to make the asymptote equal 0. Everything is to the right. How far to the right is minus 5 to 2, 7 units. And how far is minus 5 to 10, 15 units. So when I plug in 10, I get 15 sevenths. That's the base. Those differentials, those horizontal differentials. In the exponential, it was the vertical differentials that gave us the base. All right, so let's erase that. And pause the video. You try the one over there. Probably a reflection. No, not a reflection yet. But we have the inverse of decay. So I'm going to start with 2000. Left to right. How do I get to 1927? Down 73, I believe. Down 73. So now when we get a base that is a growth base, the minus sign, really flipping that base. So we have a log. Make a 0 out of the asymptote, so x minus 4. Make a 1 when we use the number 7. 7 minus 4 is 3, so now it's the number 1. And now when I drop a 12 in, 12 minus 4 is 8/3 will be the base. Okay, and that's the same thing if I made this a positive and I made this a 3/8. I'm going to get the same graph. I hope. Let me know if I'm mistaken, but I believe so. You pause the video, give you a chance to look at this. This one's a reflection. I'm going to start with y equals 50. And read from instead of left to right, I'm going to do right to left. So I'm starting with 50. How do I get to 93? 43 units. Still a logarithm, but I'm measuring from 10. And I'm measuring to the left, so I'm going to say 10 minus x. Now when I drop a 7 in, I can see that that's a change of 3. And when I drop a 1 in, I get 9/3. Let's make this a 2. Let's make this a -1. I don't like the same numbers showing up anymore. So -1 means that from 10 to -1 is backwards 11 units. And from 10 to 7 is backwards 3 units. Okay, so when I put -1 in, I get 11/3. And that should be that graph. All right. Hopefully I'm not making any mistakes. I'm certainly not checking my work, so probably making a mistake here or there. Hope not. All right, so now graphing. E to the x, instead of giving you the graph, we're going to create the graph. And I'm going to use 2 things. E to the 0 is 1. So I'm going to make my exponents. My exponent will equal 0 one time and 1.1 the next, because e to the 1.1 is approximately 3. So I can see that I've got a 3-to-1 ratio. If I pick the right numbers, there we go. So there's about 3-to-1. What makes this 0? 0. Well, first I got to get my asymptote 7. Y equals 7. So 0 gets me 7. No, 0 gets me 4 plus 7, 11. Excuse me. And now when I put 1.1, I'm going to get 12 plus 7, 19. So 1.1 is approximately 19. Okay. So e to the 1.1, show it one time, 3, roughly 3. There's your 12 plus 7, 19. We're going to do that each and every time. We're going to make the exponent 0. We're going to make it 1.1. We're going to standardize this process. All right, so I got an exponential growth again. I'm gonna make a 3-to-1 picture. What makes this thing 0? 3. My y asymptote is 6. I'm gonna add 5. 6 and 5 is 11. And then I'm gonna do 3 times 5, 15, plus 6 is 21. What makes x minus 3 1.1? Oh, roughly 4.1 on a calculator. That's a comma. That gets me 21. There's my 3-to-1. There's my up 5. There's my up 15. Okay, 3 times 5, 15. All right, so we got that one. E to the x, one more e to the x graph. This one is going to be decay. And I'm going to get a 3-to-1. Okay, what makes that 0? 2. 2 gets me 7 minus 9, negative 2. So this is y equals minus 9. And when I get 1.1, I'm going to get 3 times this. So I'm not sure which side I'm going to be on. So I just got to find these things out. Definitely putting in a 2 gets me negative 2. And if I make this 1.1, I better do it out for you. Okay, first I get 5.5. Then I subtract 2, 3.5. And I divide by the negative. Minus 3.5 is to the right, to the left of 2. So that's going to be over here. So minus 3.5 should get me 21 minus 9. 21 minus 9, 12. Okay, and so minus 9 to 12 is 21 units of change. This should be 7 units because I'm getting that 3-to-1. All right, and I said 2 gets me negative 2. And how far is it from negative 9 to negative 2, 7? Okay, so that looks good. All right, now we're going to do ln. And the ln is going to be based on, I think you can see up here. Well, the ln of 0 is undefined. ln of 1 is 0, which is the inverse of e to the 0 is 1. And the ln of 3 is approximately 1.1. Over there, we were doing 1.1, got us approximately 3. And e to the x is always greater than 0, just for the record. So therefore, I need stuff bigger than 0 in order to see the graph. So what makes a 0? Asymptote of x equals 2. And then I'm going to have exponential growth. I want x to equal 3. 3 minus 2 is 1. And the ln of 1 is 0. And 0 times anything is 0. So when I put a 3 in, I get 7. And then when I put, make this equal 3, which unfortunately is the number 5. I hate having it show up anywhere initially, but 5 minus 2 is 3. The ln of 3 is approximately 1.1, so we get 5.5 plus 7, 12.5. Roughly. That's a feel for the graph. Okay, you try the next one. I'll just do it. Negative 4 gets me 0. My graph is still the inverse of decay, inverse of growth, I mean, sorry. So I want that to equal 1. So to make it equal 1, this has to be 5, so x is 1. And the ln of 1 is 0, so it gets me 9. Nice little patterns here. Now I'll make this 3. 5 times 3, 15, minus 4 is 11. So over here we get an 11. And 3 times 7, 21, plus 9 is 30. Okay, let me make sure I did that right. So let's put 11 in. 11, 15, 3. ln of 3, 1.1. 7 times 1.1 is 7.7. Good thing I did this. 7.7 plus 9 is 16.7. Boy, did I butcher that. 16.7. Nasty. Yeah, I guess we're okay. It was pretty much a very strange argument that I gave you. All right, so this one here will take a little more time probably, but what makes a 0? Negative 6/5. Okay, I've got a subtraction, so I think I'm going to get the inverse of decay. When does this thing equal 1 minus 6 divided by 4? This equals 0 minus 6/5. Okay, that's correct. This thing equals 1. My brain's slowing down. Okay, at -1. Okay, so -1 is a little bit to the right. And which one do I want to do? I think I want to do this here, if I'm not mistaken. -1 gets me -10. Okay, and I want 5x plus 6 to equal 1.1. No, I want it to equal 3, sorry. Getting dyslexic here. So that's minus 3/5. Minus 3/5 is, so this was here. So -1, -10, and minus 3/5 is to the right of -1. I haven't done these in a while, I gather. And that's going to get me -12. Yes, that's lower than that. All right, that should be correct, I hope. If it's not, I'm not making the video again. You just write to me and say, hey, did a clunker. All right, so let's just see what we have here. Sinusoids are written from the midline, which in this case is 40. I'm going to do it as a sine function the first time through. I'll change it to cosine after so I got to go up 10 to get to 50. 1 pi, 2, 3, 4, 5 pi. I'm going to do it as a sine function. So 2.5 revolutions takes how many years? 103 years. Provided I start with 1800. And I want to be at a max, and the sine function's maxed, right? Heights go up, down, maxes out at pi/2. So I'll just sneak a pi/2 in there. Now, if I want to do it as a cosine, all I got to do is substitute cosine, and cosine is all about widths. And the width is max at a radian value of 0. As I walk around the circumference of the circle, right, where am I at a max? Stay put, over here, at 0 degrees, or 0 radius lengths. All right, I haven't moved at all. All right, so I got to get rid of that. And now I wrote that as a cosine function. Now let's do a couple more. Do it as a sine and a cosine. Infinite number of ways to write these equations. Let's erase the board. You take a look at the one up there. Okay, I'll just write it. So I'll do a sine function again, 40 to 50, 45. I'm going to do a plus. Plus 5 sine. Now, where am I at a minimum? I'm at a minimum at 3 pi/2. So I'll do it off of that. 1 pi, 2, 3, 4, 5, 6, 7 pi. Takes me 2000 to 2024, 24 years. I'll do x minus 2024. And when do I want to be at a minimum? 3 pi/2. Okay, so when we put in 2024, I'm sorry, I got to build this off of 2000. That was a clunker. All right, so when I drop in 2024, I'm going to cancel the 24s, 3.5 revolutions. So I'm starting at 3 pi/2, 3.5 revolutions. 1, 2, 3, 4, 7 pi. So I'm going to start here, 7 pi. 1, 2, 3, 4, 5, 6, 7 puts me up at the top, which is a max, which is the number 1. And that means 1 times 5 is 5 plus 45 gets me 50. If I wanted to go and base it off of pi/2, I would have had to make a negative. And if it's a cosine, I'm at a cosine, I'm at a minimum, but getting bigger. Well, that happens on this side, minimum. So I could have written minus cosine, I believe minus cosine at, lost my train of thought. I think that does it. So when I drop 2000 in, let's see, I get cosine of 0, which is 1. Take 5 away from 45, we got 40. Okay, so it did work. All right, more practice for the final here. Can you name that one? I'll just do it as a 3 pi over 2, just to get it out of the way. 20 plus 90, 110, cut in half, 55. And 55 to 90 is 45. Is that right? No, 35. That's right. I'll do a sine curve. I'll build it off of 1 pi, 2, 3, 4, 5, 6, 7 pi again. 3.5 revolutions. Taking 15, 30, very good year, 70 years. That we should look at the period of the sine function. That period appears to be from pi over 10, so a half a revolution. So that should be 20 years from top to top. From here to here should be 20. That should be 20. That should be 20. And this should be 10. Oh yeah, there's your 70 years. Oh, I digress. Building off of 1530, x minus 1530. And I want to start at a min. So I'll do 3 pi over 2. That gets me the number -1 when I put in 1600. -1 times 30 gets me. Oh no, yes, I am building this off of this. So 1530 gets me 3 pi over 2. So that's minus 35. And then 1600. I got to put this in because my brain's slowing down. 7 pi. All right, 7 pi is for the sine function. Oh, but I'm building it off of this. Yeah, building it off of this will put me up here. All right, brain's slowing down a little bit. That's all right, getting old. All right, one more. You try to name this one. I've changed the location. I'm going to build it off of a sine function. Because I'm in the middle. Oh, and going up. And we read in this direction. Right? We unwrap that, it becomes our x-axis. So, not to belabor the point, I'm going to start with 0, make it 0 out of 1950. So I'm going to build it off slightly different. Okay, I'm going to do a sine function. I know 1950 to 2024 is 74 years. And I'm going to go, that's half a revolution. So that's 1 pi, 2, 3, 4, 5 and a quarter. 5, 6 and a quarter, I believe. 6.25 pi. 6 and a quarter. 6, do I want to do it that way? 6 and a quarter, 25 fourths. Yeah, I guess I'll do 6.25 like that. The heck with it. All right, that's based off of the number 0, no trips around. I'm starting here, so you don't really need to write that. And we've got midline 20 and 36. So we're going to go up to 8. So y equals 8. And I'm measuring from 28. So 28 plus 8. Yeah, definitely slowing down here. All right, let's check 2024 real quick. 2024 minus 1950 is, this might be a half. I think I butchered that. So that would be 6.5, I believe. Okay, so the 74s cancel. So the sine is 6.5 pi. So 6 pi is here. 0.5 puts me there. Half a pi. So that's 1. 1 times 8 is 8. No, I wanted 0, right? No, I did 1 max. Yeah. So 1 times 8 is 8. Plus 28 is 36. I believe that's correct now. All right, hang in there, Jimbo. All right, so for calculus, it's real important to learn how to graph these functions. So I like to use, when there's a change of signs from positive to negative or vice versa, I like to use a dash. And when there's no change of signs, I like to use a dot. So let's just get a dotted line here. Now let's just get a line. All right, and let's put the critical numbers, -4 and 2. Dash, -4, dash 2. Why? Odd exponents. Odd exponents, x minus 2 is a linear function that changes signs from negative to positive at x equals 2. Then this parentheses changes signs at x equals -4. And I hope you can see that that's a positive. So when I put in a positive number bigger than 2, I get a positive times a positive, which is positive, so I know I'm going up. All right, so that's what my graph looks like. Obviously, between -4 and 2 is -1, and I could easily put that in, put -1 in, and we get -9. Put 0 in, and you get -8. So there's some things you can put in here very quickly. Okay, but what I'm after is sign changes, and that's really going to take place on the next one. So let's do that one real quick, getting the conversation started here. Some of you haven't even practiced these yet, where some of you already have it down. 0, dot, no sign change. 5 to an odd, sign change at 5. It's going to take on a cubic. Look, 2 is a root. -3 to the first power, dash, sign change. Put a number, huge number in here. Square it, you got a positive. Big number -5 cubed, you got a positive. Big number +3, you got a positive. So I now know that my graph looks like at 5, it's got a cubic root. So it's going to do that. No change at 0, linear root. So I've got some kind of x to the 4th, I believe, or x to the 6th is what it is, right? Even function. And that's what it basically looks like. And I thought it would be useful to say, when is y greater than 0? So -infinity to -3, union, it said didn't say or equal to, so 0 doesn't work. 5 doesn't work, but 5 to infinity does. Now, if I wanted it to greater than or equal, let's do that now. Well, then -3 works. So does 0. Brackets show that they do work. So does 5 to infinity. Okay. This is not the first time we've talked about this. We've talked about it quite a few times, but we're running out of time. Semester's coming to an end. Time to give it a little more thought. All right, so that takes care of this one. Last one, then I'll upload this video. So you're pausing the video. I'm just going to draw an x-axis here. X-axis, I'm going to put 2 down. 2. There's a dot because it's an even exponent. -5. There's a dash because it's an odd exponent. 7. Even exponent, a dot. Okay, and it looks like I've done the same thing each time. Put a number bigger than 7 in, this parentheses positive, this parentheses positive, this parentheses positive. I'm going up. That's what the graph looks like. When am I greater than? Let's get rid of the equal sign. When am I greater? When is y greater than now? Let's keep the equal. Get out of here. Upload this thing. When am I greater than or equal? Well, that works. And everything across the board works. So that's easy. X is greater than or equal to -5. Makes that true. All right, so I hope I didn't make any mistakes, and that was really just repetitive practice so that you can get the mechanics down, how to write functions quickly, because once we get the mechanics down, well, it's easier to talk about concepts. All right, so I hope that helps somebody just get a little quicker, faster, stronger. Toodaloo.